Mathematics feels abstract, cold, detached from reality. Numbers live on paper, in symbols, in human minds. Rocks, stars, and atoms feel real, in a way equations do not. And yet, again and again, mathematics describes the universe with unsettling precision. Equations written by humans predict the behavior of particles, the motion of galaxies, the bending of light, the expansion of the cosmos. This is not a small coincidence. It is one of the deepest mysteries physics has ever encountered. Why does mathematics work at all? Not why it helps sometimes, but why it works so well that reality seems to obey structures invented in the human mind. This mystery has been hiding in plain sight for centuries. Isaac Newton wrote equations that described planetary motion with astonishing accuracy. Centuries later, Einstein wrote equations that predicted phenomena no one had ever observed, like gravitational waves, which were confirmed 100 years later. Quantum mechanics relies on mathematical formalism so abstract that even physicists admit they do not understand them intuitively. Yet the predictions are accurate to more decimal places than any other theory in science. Mathematics does not merely approximate reality, it anticipates it. This is where discomfort begins. If mathematics were just a language we invented to describe patterns we observe, its success would be limited to what we already know. But mathematics consistently goes beyond observation. It reveals structures before we have any physical evidence they exist. The equations come first. Reality follows. This flips the usual relationship between theory and world. It suggests that mathematics is not just a tool for describing reality. It may be woven into reality itself. Eugene Wigner famously called this the unreasonable effectiveness of mathematics. Unreasonable because there is no obvious reason for it. The universe did not have to be mathematically elegant. It did not have to obey simple equations. It could have been messy, irregular, resistant to compression. Instead, reality appears compressible. Vast complexity collapses into short mathematical expressions. This compressibility is not guaranteed. It is a fact about our universe, and physics does not know why it is true. One response is Platonism, the idea that mathematical structures exist independently of humans in some abstract realm, and the universe happens to instantiate some of them. In this view, when physicists discover equations, they are not inventing them. They are uncovering truths that were always there. Mathematics works because the universe is mathematical. But this explanation raises immediate questions. Why does the universe realize these particular structures and not others? Why are the structures simple enough for human minds to grasp? Why should an abstract realm of mathematics have anything to do with physical existence at all? Platonism replaces one mystery with several deeper ones. Another response is instrumentalism. Mathematics works because it is flexible. We invent mathematical frameworks and keep the ones that fit. The rest are discarded. This makes mathematics look successful because we ignore failures. But this explanation fails to account for prediction. Physics does not merely retrofit equations to data. It predicts entirely new phenomena using mathematics developed for other reasons. Complex numbers were once considered useless abstractions. They turned out to be essential for quantum mechanics. Non-Euclidean geometry was a mathematical curiosity. It became the language of space-time. Group theory was pure mathematics. It became the backbone of particle physics. These developments were not guided by experimental necessity. They were mathematical explorations that later became physical law. This suggests that mathematics has an uncanny ability to map onto reality in ways we do not design. The mystery deepens when you consider how selective this effectiveness is. Mathematics works extraordinarily well in fundamental physics. It works far less well in complex systems like biology, economics, or psychology. The closer physics gets to fundamental structure, the more mathematical it becomes. This correlation is striking. It suggests that at the deepest level, reality may not be made of objects or substances, but of relations that are inherently mathematical. Space, time, fields, particles may be manifestations of abstract structure rather than primary ingredients. Physics increasingly describes the universe not in terms of things, but in terms of symmetries, invariants, and transformations. These are mathematical concepts, not physical ones in the everyday sense. The success of mathematics may reflect the fact that reality itself is structured mathematically, but this raises a disturbing implication. If reality is mathematical, then existence may not be something over and above structure. The universe may exist because certain mathematical structures exist. This is a radical idea, but it has serious proponents. In this view, the distinction between mathematical existence and physical existence dissolves. The universe is not described by mathematics. It is mathematics, experienced from the inside. This idea feels extreme because it undermines the intuitive hierarchy where math is abstract and physics is concrete. But intuition has already failed us many times. At the quantum level, particles do not behave like things. At the cosmological level, space-time behaves like geometry. Perhaps concreteness itself is an emergent illusion. Perhaps what feels solid is simply stable mathematical structure. Another possibility is that mathematics works because minds like ours evolved in a universe where mathematical regularities exist. We are tuned to notice patterns that can be compressed. Our brains are pattern-finding machines. Mathematics is an extension of that ability. But this evolutionary explanation only shifts the question. Why does the universe contain patterns compressible enough for minds to exploit? Evolution explains why we notice them, not why they exist. And the patterns existed long before minds evolved to observe them. Stars formed, atoms bonded, galaxies rotated. Mathematics described those processes even when no one was there to write equations. This suggests that mathematical structure is not dependent on observers. It is there regardless. The most unsettling aspect of this mystery is that mathematics does not care about meaning. Equations work whether we understand them or not. Quantum mechanics functions perfectly even though physicists disagree on what it means. The math runs, reality follows. Meaning lags behind. This suggests that understanding may not be fundamental. Structure is. And mathematics captures structure better than any other language we have. The universe seems indifferent to our interpretations. It responds only to relationships encoded mathematically. This reframes the goal of physics. Physics may not be uncovering a story about what the universe is made of. It may be uncovering the abstract rules that govern relationships. Matter, energy, space, and time may be manifestations of those rules. Mathematics does not describe the universe because we are clever. It describes the universe because the universe behaves like a mathematical object. This idea also explains why mathematics feels discovered rather than invented. When mathematicians explore abstract structures, they often encounter surprising constraints and truths they did not choose. Mathematics resists arbitrary manipulation. It has an internal logic that must be obeyed. That resistance mirrors the resistance physicists encounter when they try to force reality into intuitive categories. Both mathematics and physics push back. They reveal what is allowed and what is not. This parallel suggests that the two are deeply connected. Perhaps mathematics works because both mathematics and physics are exploring the same underlying space of possibilities. One does so abstractly, the other does so physically. This does not resolve the mystery, it sharpens it. Why should there be a space of possibilities at all? Why should it have structure? Why should some structures be realized as universes? Physics does not answer these questions. It uses mathematics to navigate them. The effectiveness of mathematics may be telling us something uncomfortable, that reality is not fundamentally narrative, material, or intuitive. It is structural, and structure does not need explanation in the way stories do. It simply is. This leaves you with a quiet unease. Mathematics works not because the universe is friendly to human minds, but because both minds and universes may be expressions of the same abstract order. You are not imposing mathematics on reality, you are recognizing it. And recognition feels mysterious because it blurs the line between invention and discovery. Why mathematics works at all may never be fully explained. Any explanation would itself be mathematical. The mystery loops back on itself. But the fact that mathematics works so well is not an accident. It is a clue that reality may be far more abstract than it feels, that what you touch and see is a surface manifestation of deeper, invisible structure, and that the most powerful descriptions of the universe are written not in the language of things, but in the language of relations. The universe listens to mathematics not because we tell it to, but because mathematics is already there, waiting to be noticed. This is Veritas Labs, where truth is tested.